Okay, here's a problem that was sent to us. We have a vector and a vector field with these components of F1, F2, and F3 for its I, J, and K components. And of course, these are variables that are continuously changing as we move around to different positions in the vector field. And R is the position vector, so this just points to some specific point in three-dimensional space that's going to have an X, Y, and a Z coordinate to it. And we're supposed to show that if we take the dot product of our vector F with the del operator and then have this quantity operating on a position vector, that in turn gives us our original vector F. Now, this, of course, taking the dot product in this direction between the del operator and any vector, that's the divergence of the vector. But we're doing it in this direction. We have a vector dot. So we're taking the dot product in this direction, and then we have a vector following this. Well, first of all, we've dealt with this expression in past videos. Sometimes it had a scalar following it. Sometimes it had a vector following it. And of course, this, as we've discussed previously, that makes no sense whatsoever. The del operator can only operate directly on scalar quantities. But this, and again, we've dealt with this in previous videos, that is a valid expression. So, as I said, we've dealt with it previously, but we have never applied it directly to the position vector. So, let's go ahead and do that and see if we can make sense out of this. So we have, the first part of the expression is F dot the del operator. So let's take that dot product now. Here's vector F. Take the dot product with this, our del operator. And if we take that dot product, that's what this term is, what do we get? So I dot I is 1, I dot J and I dot K, of course, are 0. So the first term is going to be then F1 times that partial derivative. So we have F sub 1 times the partial with respect to x. Now we continue taking the dot product. J dot I is 0, J dot K is 0, J dot J is 1, so we're going to have plus F sub 2 times the partial with respect to y. And we go ahead and take the K units and take those dot products. That's 0, that's 0, that's 1, and we're going to have plus F sub 3 times the partial with respect to z. So that's what this expression is right here. And then we have the position vector. So that means we're going to be taking these derivatives. Take the partial of the position vector with respect to x, take the partial derivative of the position vector with respect to y, take the partial of the position vector with respect to z. And here is our position vector with components x, y, and z. Now, these x and the y and the z, they're totally independent. They're just simply the coordinates of some point in three-dimensional space. They don't relate to each other in any way. So if we had, for example, the partial of x with respect to y, well, x does not change at all with respect to y. They're totally independent of each other, so that's 0. Or likewise, the partial of x with respect to z, that's 0. Or the partial of y with respect to x. Or the partial of y with respect to z, that's 0. So, let's go ahead then. Here's our position vector. First off, we want to take the partial derivative of this expression with respect to x. The partial of z with respect to x, that's 0. The partial of y with respect to x, that's 0. The partial of x with respect to x, that's 1. We have 1 times the unit vector I. So this just simply gives us the unit vector I. So let's write it in. This is f sub 1. Then we have plus f sub 2, the partial of the position vector with respect to y. Well, this is going to be 0, the partial of x with respect to y. The partial of z with respect to y is 0. The partial of y with respect to y is 1. So we have 1 times j. So this is going to give us the unit vector j. And likewise, when we take the partial of the position vector with respect to z, that's going to be 0, that's going to be 0. The partial of z with respect to z is 1. That gives us the k unit vector. So, this whole expression is just this, and of course this is vector f. It's component in the I direction, it's component in the j direction, and it's component in the k direction. So indeed, it looks strange, but in fact, this is a valid expression. Okay, that's all we have to say about this problem. Hopefully that clears that up. And come back, join us for some more videos, and we'll try and tackle some more problems.